Welcome to This Explainer. Today, we are embarking on the ultimate cosmic roadmap. We're going to trace what you might call the hero's journey of matter. It's a spectacular evolution that will take us from the highly stable, everyday stars that quietly illuminate our night sky, all the way to the most violent, bizarre, and literally exotic cosmic remnants in the known universe. By the time we finish up here, you're going to have a complete picture of the entire stellar family.
Okay, let's dive into this because it instantly shatters a massive cosmic illusion. You know, when we look up at the sky or just think about our own sun, it's so easy to assume that bright, golden stars are the standard. But take a look at that massive 75% slice. The vast majority of the cosmos is actually composed of tiny, dim red dwarfs. They're small, they're cool, and because they sip their hydrogen fuel so incredibly slowly, they can live for over 1 trillion years. Since the universe is only about 13.8 billion years old, that means not a single red dwarf ever created has actually had time to die yet. They are, without a doubt, the silent majority of the universe. To make sense of all these incredible celestial bodies, we've organized our 19 different stellar objects into 4 distinct evolutionary categories: the mighty dwarfs, giants and supergiants, dense stellar remnants, and finally, black holes and exotics.
Starting off with Category 1, the mighty dwarfs. These are the everyday engines of the universe.
Let's look at the main sequence of dwarfs. We already talked about the incredibly long-lived red dwarfs on the left. But look right there in the middle column, orange dwarfs. These sit right between red dwarfs and stars like our sun. They are highly stable and absolutely fantastic candidates for hosting habitable planets. They produce fewer dangerous flares and live for a massive 15 to 30 billion years, which gives life plenty of time to develop. And then on the right, we have the yellow dwarfs. This is where our sun sits. They burn at around 5,000 to 6,000 Kelvin and have a lifespan of roughly 10 billion years. Since our sun is about 4.6 billion years old, it's basically sitting right at its midlife crisis point. So what exactly happens to a yellow dwarf like our sun? Let's move to this step-by-step sequence and see how this builds. In about 5 billion years, it'll run out of fuel and swell up into a red giant. After that, it entirely sheds its outer layers, and the remaining core collapses into a white dwarf. That's a super dense object roughly the size of Earth, but packing the mass of the entire sun. Over billions of years, it's just going to sit there, slowly cooling off, until it theoretically becomes a dark, freezing black dwarf. I say theoretically because, again, the universe literally isn't old enough for one of those to even exist yet. To quickly round out the dwarf family, we have a few real oddballs. First, brown dwarfs. These are essentially failed stars. They just didn't gather enough mass to sustain normal hydrogen fusion, though they can fuse heavy hydrogen, or deuterium. They gradually cool over time, making some of them cooler than certain planets. Then we have blue dwarfs, which are a totally theoretical future phase for those red dwarfs once they finally start running out of fuel. And lastly, subdwarfs. These are incredibly ancient, dim stars with very low metal content. They just hang out in the galactic halo, serving as these cool reminders of the very early, metal-poor history of the universe. Moving right along to Section 2, giants and supergiants. These are the stars living fast and dying very young. Now we are looking at 2 very different types of giants. These are the massive, highly volatile stars that burn furiously, and they have lifespans measured not in billions, but in mere millions of years. On one side, we have red giants. These are stars that have completely exhausted their core hydrogen. They expand dramatically, which actually drops their surface temperature to a cooler 3,500 to 5,000 Kelvin. When our sun reaches this stage, its expanding shell will literally engulf Mercury and Venus. No way around it. On the flip side, we've got blue giants and blue supergiants. These things are intensely hot. We're talking up to 50,000 Kelvin, and they shine hundreds of thousands of times brighter than our sun. They are burning their fuel at an absolutely terrifying rate, basically racing toward a catastrophic end. The extreme ends of these massive stars are just staggering. Red supergiants are the absolute largest stars by volume in the known universe. Take Betelgeuse, for example. If you dropped it exactly where our sun is right now, its surface would swallow Mars whole and might even reach out to Jupiter. Then you have Wolf-Rayet stars. These are exposed helium cores that have totally lost their outer hydrogen layers. They're unimaginably hot, sometimes over 200,000 Kelvin, and they blast out these intense stellar winds at 2,000 kilometers per second. That's so fast they carve out these incredible, highly visible nebulas all around themselves. And this brilliantly illustrates the sheer mind-numbing scale we are talking about. 1,700. That is the radius multiplier of UY Scuti, a red hypergiant, compared to our own sun. Hypergiants are the most luminous and massive stars known, pumping out millions of times more light than our sun. But because they're so huge, they are highly unstable, and they almost always end their brief, violent lives in one very specific, spectacular way.
Which brings us to Category 3, dense stellar remnants, the awesome aftermath of supernovas.
So, the bridge between a giant star and a dense remnant is, of course, a supernova. It is the catastrophic, violent explosion that literally tears a massive star apart when it can no longer fight back against the crushing weight of its own gravity. The outer layers are blasted clear across the cosmos, but the core collapses into something that completely defies common sense.
A neutron star presents an extreme contradiction. Picture a sphere only about 20 kilometers across. That is roughly the size of a single city. Yet packed into that tiny space is up to 2.1 times the mass of our entire sun. They are composed almost entirely of neutrons, compressed so tightly that protons and electrons just merge together. To put that density into perspective for you, a single teaspoon of a neutron star, if brought to Earth, would weigh 6 billion tons. The gravity on its surface is 2 billion times stronger than what you're experiencing in your chair right now.
And neutron stars spin. Oh boy, do they spin. Sometimes hundreds of times a second. When they emit these sweeping lighthouse beams of electromagnetic radiation from their poles, we call them pulsars. And there is an amazing piece of human history here. When Jocelyn Bell Burnell discovered the very first pulsar back in 1967, the pulsing signal was so unbelievably precise, so perfectly timed, that researchers briefly nicknamed it LGM1, which stood for Little Green Men. They genuinely had to stop and consider if they were picking up an artificial beacon from an alien civilization.
But wait, it gets crazier. Enter the magnetar. These are neutron stars with magnetic fields up to a quadrillion times stronger than Earth's. Just think about that. If a magnetar was floating halfway between the Earth and the Moon, its magnetic field would instantly wipe the data off every single credit card on our planet. In 2004, a magnetar called SGR 1806-20 released a massive flare. In 1/10 of a second, it blasted out more energy than our sun produces in 100,000 years. That flare literally disturbed Earth's ionosphere, and it came from 50,000 light-years away.
Finally, we arrive at Category 4, black holes and exotics. We are now at the absolute edge of physics.
So, the crucial point of no return here is the event horizon. When a star with more than 20 solar masses dies, its collapse doesn't just stop at the neutron star phase. The gravity becomes so overwhelmingly strong that it literally punctures the fabric of space-time. The event horizon is that boundary beyond which escape is mathematically impossible. Not even light can get out. These objects range from smaller stellar mass black holes all the way up to the supermassive monsters lurking at the centers of galaxies. Think of the billions of solar masses giant in galaxy M87, which we miraculously managed to capture the first ever image of back in 2019. But as we approach the end of our explainer today, I really want you to consider a massive gap in our understanding. What happens in the gray area? What lies exactly between the crushing density of a neutron star and the infinite light-trapping void of a black hole? Does matter just give up immediately? Or is there some bizarre intermediate step we are missing? Well, the answer might just be quark stars. This is a hypothetical state where the pressure inside a dying star is so incredibly extreme that the neutrons themselves shatter apart into their most fundamental building blocks, quarks, forming a strange, ultra-dense soup called quark matter. It would be smaller and denser than a neutron star, but just shy of collapsing into a full-blown black hole. Back in 2002, the Chandra X-ray Observatory spotted two mysterious objects that looked way too small to be neutron stars, but too large to be black holes, making them really tantalizing quark star candidates. Their existence is still totally unconfirmed, which leaves us with a provocative final thought for today. We've mapped out everything from tiny red dwarfs to supermassive black holes. But what other bizarre, completely unconfirmed states of matter are still out there, hiding in the dark, waiting to rewrite our physics textbooks? Keep wondering, and thanks for exploring the Stellar Menagerie with us.